Hello everyone and welcome back. Today in this lecture I am going to cover a very important topic of graph theory that is related to isomorphism. So we will discuss in details about isomorphism and what do we mean by isomorphic graphs. Before we go into the very definition of isomorphism, let's understand the concept with the help of an example. So here I have two graphs G and H. Now in the very first sight we can see that the two graphs look different. So it seems they are different graphs. But if we observe the graphs very carefully and if I try to draw the first graph, that is G, in a different orientation so that the structure of the graph G matches with the graph of H. So let us see if we can do that. Okay. So if I start redrawing my graph G just like the way H is drawn, so I will have my vertex A suppose here and the vertex B here. Okay. Now in order to match the graph G with the structure of the graph H, instead of drawing the vertex C at this position, I will draw the edge AC and hence the vertex C over here, so that the adjacencies of the graph G are maintained in this redrawing, but structure wise it is going to look similar to that of H. Now what about the vertex D? Let us keep the vertex D here, and as per the adjacencies present in the graph G, B and D are adjacent, so I draw this edge, and again C and D are also adjacent, so I draw this edge. So you can see I have just redrawn the graph G, maintaining all the adjacencies and everything, but orientation wise it is different, and now the orientation of my redrawn graph G only matches with that of H. So although in the very first sight the graphs G and H look totally different, but it is possible for me to redraw one of the graphs and make it look exactly similar to the other one, right? Such pairs of graphs which look orientation wise different but can be redrawn and are nothing but the same graph actually, such types of graphs are called isomorphic graphs to each other. And whenever we deal with such pairs of isomorphic graphs, there always exists a bijective mapping between the vertex sets of the two graphs. Let's see how. So the moment I have redrawn the graph G in the same structure as the graph H, now I can see that both the structures for this new redrawn graph G and our given graph H are exactly same. So I can now map every vertex of the graph G to a certain vertex of the graph H. For example, the vertex A of the graph G can be mapped to the vertex U. So as per the two figures of G and H, I will just see which vertex of G is acting as an image to which vertex of H. So I can see the vertex A in G is having the image U in H. Similarly, the vertex B in G is having the image V in H. C is having the image X and the vertex D is having the image W. So there exists a bijective mapping F. This F is the bijective mapping 1, 1 and onto function that will map the vertex set of the graph G to the vertex set of the graph H. This bijection F is called isomorphism. Okay, so basically between a pair of graphs, if it is found that although they look different, we can draw one of the graphs in exactly the same structure as the other, and then after we have redrawn the graph so that both of them have the same orientation, then we can easily see which vertex of one graph is mapped onto which vertex of the other graph. So we can easily construct our bijection F. This bijection is called isomorphism and the pair of graphs are called isomorphic graphs. Let's see one more example to get this concept much more clear. So here also we are having two graphs G and H. Obviously they look quite different in the very first sight. Now let's see if we can redraw one of the graphs exactly in the manner of the other. So let's pick G to be redrawn. You can pick any of them. I am picking the graph G and I will redraw the graph. Okay, just remember you are only redrawing the graph, you are not changing any property of the graph G. Okay, all the adjacencies will remain same. A is adjacent to B here and not to C, D, E, F. So the same will be maintained in the redrawn graph. Nothing will change, only the positioning of the vertices might change, the orientation might change. Okay, so what I will do, I will try to redraw G and at the same time I will keep my eyes on the graph H so that G can be redrawn in the same structure as H. So as I can see, C, F, E, D, C. this is a C4 present in my G, and a similar C4 I have in H, that is U, X, W, V, U. So I will try to first keep my C4. So I have my C4 as in G. I just keep it in the same manner. Okay. Now I can see in H, Y is a vertex, so that Y is adjacent to both U and V. Similar type of vertex is there in the graph G also, which is actually B. Okay. So instead of drawing B outside, what I will do, I will draw the vertex B inside, as Y is present in H. And B and C are adjacent, so I make B and C adjacent here. Again B and D are adjacent, so I draw the edge BD. Again, I can see in my graph G, B is adjacent to the vertex A. So I draw that edge BA in this manner, so that structure wise my graph G appears like H. Okay. Now see what I have done. I have redrawn the graph G, only the orientation has changed. So basically what I have done is, this particular area of the graph which was outside, I have just moved it inside, so that it has the same structure as the graph H. And I can see now the redrawn graph G and the given graph H are exactly the same. So basically G and H are the same graph, but they were drawn in a different orientation, so they look different. Therefore G and H are isomorphic graphs. And how do we represent this isomorphic property? By notation, G is isomorphic to H. This is how we say the two graphs are isomorphic. This is the notation for isomorphism. And to find that isomorphism, the bijection, so we will represent it by a function. You can represent it by any name of the function. We generally use the letter F for functions. So now you see the redrawn figure of G and the given graph H. So you can just easily map the corresponding vertices. C is mapped to U, D has the image V, B has the image Y, A has the image Z, F is mapped to X, and E is mapped to W. This is the isomorphism. Now we will go through the definition of isomorphism. So two simple graphs. So you can remember that we will be dealing with simple graphs only, no loops and multiple edges. So two simple graphs G and H are said to be isomorphic to each other, and hence denoted by this notation if there exists a bijection F from the vertex set of G to the vertex set of H, such that if U and V are adjacent in the graph G, that is if UV is an edge in G, then F of U, F of V, that is the images of the corresponding vertices U and V, will also be adjacent in the graph H, and vice versa. So this is exactly what we have seen in the examples. And if such a bijection exists, then that bijection F is called isomorphism from the graph G to the graph H. Now let's go through some more examples. Here we have two graphs G and H. So let's see if we can redraw one of the graphs in the form of the other. So I pick G, which is to be redrawn. So let's start. Now see, observe the two graphs very carefully first. Take 2 minutes and observe the vertices, observe the degrees of the vertices, the adjacencies, and then start redrawing. Okay. Now what I am trying to do is redraw G in the form of H. So I can see in place of Y, if I want to put a vertex in the graph G, I have to put a vertex which is of degree 3, because Y is of degree 3. Okay. So in the graph G, I can see A is a vertex which is of degree 3. So I can put my vertex A in this position, similar to the position of the vertex Y. Next, what? Y is adjacent to U, Z and X, 3 vertices. Here I can see A is adjacent to B, E and D. So I will draw the adjacencies just like the way it is drawn in the graph H. So these will be the 3 adjacencies of the vertex A. Now A is adjacent to B, E and D. So you can put the names randomly, B, E, D. Okay. Later on, while we proceed with the diagram, if we need at some point to change the positions of these vertices, then we can definitely do that. So for the time being, I have kept the positioning as B, E, D in this way. Now we can see U is adjacent to V in the graph H, and B in the graph G is adjacent to the vertex C. So I can draw my vertex C in this position. Now in the graph H, this vertex V is adjacent to the vertex Z. So in the redrawn figure of G, I need to make C and E adjacent to match the structure of H. But in my original graph G, C and E are not adjacent. This vertex and this vertex, C and E are non-adjacent vertices. So I cannot draw the edge CE in the redrawn figure because I am not changing any adjacencies. I am just redrawing it in a different orientation. All the adjacencies will remain intact. So what do I need to change then? Then again I will go back to the situation where I had some options of placing the vertices B, E and D randomly, and I have chosen one particular position for them. For example, suppose I exchange the positions of B and E. I keep D as it is. This is what I can do. I can have several other combinations also. So I have to check for all the combinations as long as I get my desired figure. So if I do this change, then what happens? I can see in the graph G, E is adjacent to the vertex F. So I can draw my vertex F here so that the adjacency in the graph G is maintained and the structure of H is also maintained. Now again, to maintain the structure of the graph H, F and B should be made adjacent, but F and B are non-adjacent vertices in the graph G. So again, this does not help. Again, I go back to the positioning of the vertices B, E, D, and what I do, I put D vertex here because putting the vertex B or E at this position was of no help, and I suppose put B here and E here. Okay. Now when D is here, I can see in the graph G, D is adjacent to the vertex C. So I can place my vertex C here. Okay. Now in the graph G, C and B are adjacent. So C and B can be made adjacent with the help of an edge. So this is basically what I was wishing for. Next, I can see C and F are adjacent in the graph G. So I can put my vertex F here so that the adjacencies are maintained, and F and E are also adjacent in the graph G, so F and E are made adjacent in the redrawn figure. See, after so much of effort, finally I could draw my graph G in a different orientation but not changing any of the properties, not changing any of the adjacencies, and therefore I get the figure of G similar to the figure of the graph H. That means G and H are isomorphic graphs, and the corresponding isomorphism would be the vertex A has the image Y in H, B is mapped to Z, C has image V, D has image U, E is mapped to X, and the vertex F is mapped to W. This is the isomorphism. G and H are isomorphic graphs. Again, we have a pair of graphs G and H. Let's see if they are isomorphic to each other or not. So here we can see the graph G is a bipartite graph, which is clearly visible from the orientation, from the appearance of the graph, that it is a bipartite graph. Now if G and H are isomorphic to each other, then H should be the same graph as G, only the orientation is different. So in that case, H should also be a bipartite graph as G is a bipartite graph. So here I now pick H to be redrawn so that I can see whether H can look like G or not. So let's check if H can have that bipartite structure. So let's start with the vertex U over here in the same position as A, that we can do because A has degree 3 and the vertex U in the graph H also has degree 3. So I can imagine U to be in a position of A. If required sometime later, I can change the vertices. So U is here. Now U is adjacent to the vertices V, X and Z. So I will make U adjacent to 3 vertices, one here. Maintaining the structure of the graph G, I will draw the adjacencies. So U is adjacent to V, it is adjacent to X and it is adjacent to Z. Next, come to the vertex V. So V is adjacent to W, Y and U. So V here already is adjacent to U. It should be adjacent to W and Y. So I draw the vertices W and Y here, so that it matches the structure of the graph G. Now W is adjacent to V, Z and X. So W will be adjacent to V, which is already there. It should be adjacent to Z and it should be adjacent to X. Next, Y should be adjacent to Z, V and X. So Y is made adjacent to Z, it is already adjacent to V, and we make it adjacent to X. If you see the adjacencies of other vertices also, X is adjacent to Y, U and W. Here X is made adjacent to Y, U and W. So if you observe, all the adjacencies present in my graph H are drawn in this redrawn figure of H. Okay, and it looks exactly the same as the graph G. So this is how we check if a graph can be redrawn in the form of the other. So here also G is isomorphic to H, and the mapping you can write easily that U is mapped into A, or you can write it in the other way around also, f of A is equal to U. It's up to you. Okay, f of V is D, f of W is B, f of X is E, f of Y is C, and f of Z is F. Next we have again two graphs G and H. So let's see if they are isomorphic to each other or not. Take a minute, observe the graphs carefully. Before you start redrawing a graph, see if their order is same, check if their size is same, check if the degree sequence is same. Okay, so in the graph G I have 6 vertices and 7 edges. In the graph H I have 6 vertices and 7 edges. The degree sequence of the graph G is 4, 3, 3, 2, 1, 1, and in H it is 4, 3, 3, 2, 1, 1. So they have the same degree sequence as well. Similarly, you can check for other properties if you can find. For example, you can see if both the graphs are bipartite or not. You can also check if they have the same number of similar type of cycles, and there are so many properties to check. So having checked the first few standard properties which are same, we can now proceed to redraw the graph. So if we initially find that the order is not same, or the two graphs don't have the same size, okay, or the degree sequence doesn't match, then definitely the two graphs are not the same graphs, and therefore you don't need to redraw the graph at all. You can just say they are not isomorphic. So here we have seen the initial few properties have been checked and they are both similar in the two graphs. So I will proceed now to redraw. So let's pick G and let's redraw G if we can in terms of H. Okay. Now see, in G and H there is only one vertex which is of degree 4. In G, D is the vertex, and in H, Y is the vertex. So when I am redrawing my graph G, first I will fix the position of that unique vertex which has degree 4, because there is no other vertex of degree 4, so I don't have any option for that. So I fix my vertex D in the same position as the vertex Y. Now I can see D is adjacent to 4 vertices as Y is adjacent to. So I draw the 4 adjacencies of D just in the same manner as it is drawn in the graph H. So these are the 4 adjacencies of the vertex D. Okay, now we will label the vertices. So I can see D is adjacent here to 2 pendant vertices E and F, but in the graph H, Y is adjacent to only one pendant vertex, and the remaining 3 neighbors of Y are non-pendant vertices, right? Now see, this is the dissimilarity between the two graphs. Let's check again. Both the graphs have a vertex of degree 4 and only one vertex of degree 4. D is that vertex in G and Y is that vertex in H. And in G I can see this vertex of degree 4 has 2 neighbors who are pendant vertices, who are of degree 1 each. But in graph H, this vertex of degree 4 Y is adjacent to only one pendant vertex and the remaining are non-pendant vertices. So this is a property that does not match between the two graphs, and hence we cannot redraw the graph G in the similar fashion as the graph H. They are varying in their properties. Therefore, I can immediately conclude that G is not isomorphic to H. This is how we represent it, and hence we cannot find any isomorphism between the two graphs. Next, we have two graphs G and H. So if you check for the initial properties, you will find both the graphs have the same order 6, they have the same size 8, and the degree sequence is also same, that is 4, 3, 3, 2, 2, 2. So here also there is only one vertex of degree 4 in each of the graphs. In G, B is the vertex of degree 4, and in H, V is the vertex of degree 4. So let's redraw suppose G and check if it can be redrawn in the form of H. So first I fix the position of the vertex B, which is the only vertex of degree 4 in the graph G. It will be in the same position as the vertex V in H. So B is adjacent to A, F, E and C. So I will keep the neighbors of B, one on this side, another on this side, another here, and lastly I will have a neighbor here. Just like they are present in the graph H, I have just located them in the same locations. But who are the vertices that B is adjacent to? They are A, C, F and E. So I now need to place the vertices. I now need to label the vertices. Now I can see E is a vertex of degree 3, F is a vertex of degree 3. In the graph H, Z and X are the vertices of degree 3 who are the neighbors of V. So definitely F and E should take these positions. Maybe F and E will be in this form, or this will be E and this will be F. So for the time being I put F here and E here. Next A and C. So I randomly put A here, C here. Now Let's proceed. As I can see, A and F are adjacent in my graph G, so this edge has to be drawn. Again, I can see in the graph G, C and E are non-adjacent vertices. So definitely I cannot draw this particular edge in the graph. Okay, this cannot be drawn. And then the structure will not match with that of H. So what I will do is, I will change the position of F and E. So let's put E here and F here. Now let's see. So in the graph G, A and F are adjacent, but for that I need to draw this edge, and therefore the structure wise it will not match with the graph H. So I cannot do that as well. So I have visited all the possibilities that I can, and I have seen that in no way I can redraw the graph G so that the structure matches with the graph H. So it is not possible to redraw the graph G in the form of H, that is G is not isomorphic to H. I'll give you a reason for that. See, the degree sequence of the graphs is 4, 3, 3, 2, 2, 2, right? So there is only one vertex of degree 4, that is B in the graph G. It is adjacent to the vertices F and E, both are of degree 3 each. And we can see in the graph G, these two vertices which are of degree 3 are adjacent to each other. But if you see in the graph H, then V is the vertex of degree 4, which is adjacent to the two vertices of degree 3, but these two vertices of degree 3 are non-adjacent in the graph H. So this is where the dissimilarity occurs. That is the reason the two graphs are not isomorphic graphs, and hence there is no bijection or no isomorphism. Next we come to these graphs G and H. So you can check their order, size and the degree sequence, they are all same. Now let's proceed to redraw one of the graphs. So let's pick G and redraw it in terms of H, in the form of H, if we can do that. In H, this vertex U is of degree 3. So when I will redraw the graph G, the position of this vertex corresponding to the vertex U should be taken by a vertex which is of degree 3 in G. So I can see F is a vertex of degree 3 in G. So I can keep my vertex F for a temporary position corresponding to the vertex U. Now F is adjacent to the vertices A, E and G. So I just draw the neighbors of F in the same locations as the neighbors of U in H. So these are the three neighbors of F. F is adjacent to A, E and G and all are of degree 2. So I can just randomly put it first. So I put A here, I put E here and I put G here. Okay, now let's proceed. So I can see A is adjacent to the vertex B also in the graph. So by that idea, B should be here to match the structure of the graph H. B is adjacent to G in the graph, but B, if made adjacent to G here, doesn't match with the structure of H. So definitely B shouldn't be here. If B shouldn't be here, then definitely A shouldn't be here. So the random positioning that I had done for A, E and G should be changed. So I have put my A here and suppose I put my E here and my G is suppose here. Okay, let's see how it goes. So E is adjacent to the vertex D in the graph. So I have to take my D here. D is adjacent to the vertex C. So I can take my vertex C here. C is adjacent to the vertex B. So I can take my vertex B here. See, structure wise till now it matches with the graph H. Now B is adjacent to the vertex G. So BG are made adjacent. Still my structure is fine. And finally A and B are adjacent. So I have to draw this edge. If you observe carefully, all the edges of the graph G are drawn and I can see G matches exactly with the same figure as H. So I can say G is isomorphic to H and the bijection will map all the vertices. For example, the vertex F is mapped to the vertex U, the vertex A is mapped to T, G has the image Z, E has the image V, D is mapped to W, C is mapped to X and B is mapped to the vertex Y. Let's come to this particular example. So here I can see both the graphs G and H have the same order, same size and the same degree sequence. You can check that yourself. Let us proceed to redraw the graph G in terms of H if it is possible. So I can see U is a vertex of degree 3 and A is also a vertex of degree 3, which is adjacent to three vertices B, E and D, and all are of degree 3 each. Here also U is adjacent to V, Y and X, all are of degree 3 each. So I can just place my vertex A in the same position as it is in G and it will match the position for the vertex U. Now the three adjacencies of A, one should be here, one should be here as per the structure in H and one should be here. Now the vertices are B, E and D. the neighbors of A. So B, E and D should be placed. So let me just place B, E and D. Now the vertex E is adjacent to the vertex F. So I must draw the vertex F at this position so that the structure of H is maintained. Again E and B are adjacent in the graph, so I have to draw this adjacency, but that will not match with the structure of H. So again I have to go back to the situation where I had an option to place my vertices B, E and D. Now I will suppose place E here, B here and D here. Now let's see. So again I can see B and E are adjacent in my graph, so I had to draw this edge, but this will contradict the orientation of the graph H. So again I see I cannot put B and E in these positions, so what I do is I place my vertex B here and D comes here, for example. Now in the graph G, I can see D is adjacent to F, D is adjacent to the vertex C, F and C. So D will have its adjacencies with a vertex here as per the structure in H and with a vertex here. So these two vertices should be C and F. So suppose I put C here, F here. Now in the graph B and C are adjacent, so I make B and C adjacent. So far so good. Now B and F, I can see in the graph G, B and F are non-adjacent vertices, but B and F should be adjacent in order to maintain the structure of H. So again I arrive at a dissimilarity. So what else can I do is I can change the position of F and C. Now if I do that, now F and B in the graph are non-adjacent vertices, but F and B in this redrawn graph must be adjacent to match the structure of H, but that I cannot do because I have to maintain the adjacency of G. So again this doesn't help. So what can I do is again I can go back to the options where I can place my vertices E, B and D. So now I place my vertex D here, then suppose I place my vertex E here and B is here. Now again I can see that in the graph B and E are adjacent vertices. These two vertices are adjacent. But if I make B adjacent here, the structure doesn't match with that of H. So again I change these two positions of B and E. Explore all the possibilities that I can have. Okay. Again if I do this, then again this same problem arises that B and E are adjacent vertices in the graph, and if I make them adjacent, then the orientation doesn't match with H. So basically I have checked all the positioning that can happen between the vertices D, B and E, and for any possible positioning I cannot match the structure with that of H. Finally, I get stuck at some point. So I will say G is non-isomorphic to the graph H, and hence there is no such isomorphism or bijection here. I hope the concept is quite clear to you. For your practice, I am posting here a problem so that even if you have any doubt, you can just clear it out by practicing some problems like this. So here I have drawn 4 graphs G1, G2, G3 and G4. What you will do is you will check for every pair of graphs here whether they are isomorphic or not. So you check whether G1 is isomorphic to G2, whether G1 is isomorphic to G3, whether G1 is isomorphic to G4. Again you check if G2 is isomorphic to G3, G2 is isomorphic to G4 or not, G3 is isomorphic to G4 or not. So every possible pair you just check on your own for isomorphism. Okay, let me just tell you all the graphs that are given here, they have the same order, same size, same degree sequence. So you can go for redrawing one of the graphs in form of the other and check for isomorphism. I will discuss the solution to this problem in the very beginning of the next lecture. So I really hope that you understood the concept of isomorphism quite a bit. Keep solving some problems. Still, if you face any doubt, any confusion, you can always write to us in the comment section below. I am going to meet you again soon with the next lecture of the series. Till then, thanks for watching, and if you love learning with me, then please do like, share and subscribe to our channel. Till then, take care. Bye-bye.